In this video, we're going to talk about gas mixtures because when you actually encounter gases, they're hardly ever pure. They're usually mixtures, and air is a good example where air is 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and there's a lot of other trace gases in there. Now, we're dealing with ideal gases, and the great thing about ideal gases is that molecules don't interact with each other. They're more or less visible to each other. So, in talking about ideal gases, we can say, they act independently of each other. They don't see each other. They're ghosts to each other. So let's talk about this idea of partial pressure. So if you have a mixture of gases, when you're talking about a partial pressure, you're saying the pressure due to this one type of gas. So, for example, I could talk about the partial pressure of oxygen in air. Now, let's take air as our example again. So we have a gas mixture with a lot of stuff in it. And you calculate partial pressures by just this equation. It's the ideal gas law. It's the pressure of, let's say, nitrogen, and that's equal to the moles of nitrogen multiplied by RT divided by volume. Ideal gas law. Do the same thing for oxygen, argon, carbon dioxide, and everything else. So to calculate partial pressure, since they don't interact with each other, you're just doing the ideal gas law, and you're using the number of moles of that type of gas. And Dalton's law of partial pressure says the total pressure of your system is equal to all your partial pressures. Makes sense, right? So let's say we have a balloon full of air. Well, the pressure inside of that balloon is just all the partial pressures of our components. Now, what I'm going to do here, it looks like a lot of math, but it's not too bad. What I'm going to do is I'm going to combine two equations. The equation to calculate the partial pressure for each type of gas, and Dalton's law to make one total equation. And that's how I would calculate total pressure. Now, if you notice, all these terms have RT divided by V. So what I'm going to do is I'm just going to pull that out, and I'm just going to have number of moles of N2 plus O2 plus argon plus CO2 multiplied by this RT divided by V. And I can say all these moles of gas, that's just the total moles of gas we have in our system. So how do we get partial pressure now? So let's say I want to find the partial pressure of nitrogen. Well, the partial pressure of nitrogen divided by the total pressure equals the number of moles of nitrogen divided by the number of moles total. And that's because we have this relationship where the number of moles of N2 multiplied by RT divided by V divided by the number of moles total multiplied by RT divided by V equals this pressure. So this might all look very confusing, and there's a lot of math and a lot of terms going around. But this is the point I want you to come across with. The partial pressure of a gas is just equal to the number of moles divided by your total moles. And it's all because of the ideal gas law. And this quantity, moles of one type of gas divided by total moles, we call that the mole fraction, or Chi-A. So we can use this type of math for any gas. And to get the partial pressure, it's just partial pressure equals your mole fraction times your total pressure. That's all you have to do to calculate partial pressures. So let's try and do an example of this. Let's say we're at 1 atmosphere. And let's say nitrogen takes up 78% of our volume. So the mole fraction is 78. So the partial pressure due to nitrogen in atmosphere is 0.78 times 1 equals 0.78. Oxygen would be 0.21 atmospheres. argon 0.009, and carbon dioxide 0.0004 atmospheres. And you might be wondering, how did I go from percent volume to moles? Again, that's just the ideal gas law. PV equals nRT. Pressure is the same, R is the same, T is the same. So volume equals the number of moles. So our total pressure when we add all four of these up is 0.9994. And that's due to rounding, not taking into consideration like water vapor and other trace gases. But if we round up, we get 1 atmosphere back. Now let's talk about oxygen. So as you saw, our atmosphere is only 21% oxygen. And that is what our lungs are designed to handle. Our lungs work best at a pressure of 0.21 atmospheres of oxygen. But let's say you like to climb mountains, and as the higher you go up, the partial pressure of oxygen becomes less. So at the peak, you have 0.065 atmosphere. And there you have a loss of oxygen, so you get dizziness, headache, and shortness of breath. While the opposite can be true if you have too much oxygen. So let's say you're a deep sea diver and the pressure of oxygen is higher than 0.21 atmospheres. You can get oxygen toxicity. So you get muscle twitching, tunnel visions, convulsions, and that's really bad if you're diving under the water. And too much N2 can be a problem too. So we're designed to work with 78% N2. While if you get too much, you can get narcosis. It's called rapture of the deep. Basically, you're diving and you feel drunk. Not great. But here's just shows you like our range of safe atmosphere. So at maximum, you can only take roughly 1.6 atmospheres of oxygen. Any more than that is oxygen toxicity. You can not really go much further lower than 0.21. That's why we get very winded even if we go up short amount of distances, short elevation. So in a lab, if you're working with gases, you're usually going to use something like this to collect that gas. So here we have zinc plus hydrochloric acid making zinc chloride and hydrogen gas. And what's going to happen in this apparatus is going to go through the tube and it's going to boil up into this water, and you're going to have hydrogen plus water vapor. And water vapor, the pressure due to water vapor, we just call that vapor pressure. So you've probably heard this if you are interested in weather, where they talk about vapor pressure. That's just the partial pressure due to water. Very temperature dependent, and it increases with temperature. So let's see if we can use this idea. So we have a gas mixture, and each of the following gases have this partial pressure. Nitrogen, 0.282. Oxygen, 0.314 atmospheres. Helium, 0.154 atmospheres. 1, tell me what the total pressure of this mixture is. And 2, tell me what mass of each gas is present in a 1.35 liter of this mixture at 298 Kelvin. So try and figure that out. Pause the video, see if you can work it out. Come back when you have an answer. Alright, let's take a look at how to do this. First, the total pressure should be simple. All you do is you just add up all your partial pressures. So our total pressure is 0.570 atmospheres. Now let's look at the amount of mass in each gas, for each gas. To do that, we have to figure out the moles. So let's go back to the ideal gas law. PV equals nRT. Well, I want to use that to solve for moles, because from moles I can get to weight. So the pressure due to nitrogen is 0.282. Our volume is 1.35. Here's our gas constant multiplied by temperature. And you see we have 0.0156 moles of nitrogen. Now I'm going to convert that into a weight using the molar mass of nitrogen, which is 14. So moles cancel out. I'm left with grams of nitrogen. So my weight of nitrogen is 0.218 grams. And I'm going to do the same exact thing for the other two gases, where oxygen is 0.118 grams of oxygen, and helium is 0.0340 grams of helium. Sorry for the formatting there. And that is how we use partial pressures in an equation. And that's all we have for this video, and I will see you in the next one.